Okay, so an additional interesting aspect, we've talked about a certain kind of number, right? We talked about natural numbers, whole numbers, integers, and then we got into rational numbers. Now, rational numbers are a specific set of numbers. Typically, we think about fractions. Because if you remember, the actual definition of a rational number is that it can be written as x over y, where x and y are integers, and y is not allowed to equal 0. Okay? So those are the basic facts about a rational number. And fractions are ways that we deal a lot of times with these numbers. But not all rational numbers are fractions. Okay? Which means that there are just regular rational numbers out there that we can deal with in different ways. So we think about it, and these break the rules about fractions and make people highly uncomfortable, to be quite honest. Okay? So these are ratios. Okay? Fractions deal with parts of a whole. Okay? Ratios can be part of a whole, but you can also compare part to part. Okay? So it's really interesting when you think about this. Fractions fit here, and they don't fit here. This is a comparison between two parts. So a ratio that I can write is, say, 2/5. If I write that as part to part, it's 2/3. Okay? So here, that means that I have 5 parts per whole. And having 2/3 means I have 2 parts, and this could still be my parts, and then this is my other parts, or parts I don't have. Or I'm comparing two groups, okay? So if you think about a class that has 14 boys out of 30 students. Okay? Now, ratios especially, because they're representing something different, aren't always going to be reduced right away in the same way. They can, okay? And the ratio is still true. But here, when I'm dealing with actual numbers, I'm dealing with 14 individual boys and 30 individual students, okay? I can talk about the ratio and comparing them, and that's the simplified setup. But I don't always want to do that. Sometimes I really need my full numbers, okay? So reducing doesn't have the same need and necessity that it did with fractions, okay? Now, as I'm looking at these parts to the whole, if I have 14 boys, I have 16 girls. Okay? Now, this same ratio can be written the other way. I can even compare whole to parts. But a lot of times it's like, well, why do that? We're not as comfortable with that. Even going parts to parts. Okay? Now, why would I leave this as parts to parts? Well, this is my classroom, and right next door, there's another classroom, and it has 12 boys out of 20 students. Okay? And so that means that it has 12 boys compared to 8 girls. okay? As I'm looking at this setup, if I were to combine these two groups, okay, combining two groups means that I'm adding them. I'm going to get a new ratio. I'm going to get 26 boys to 24 girls. Now, when I combine these two groups, these fractions, I just added straight across. But I can't do that with regular fractions because of how and what they represent. Okay? This, representing a different set, can be used in a different way. Okay? And that means that the operations function differently. Okay? Now, in the end, I may still want to know what the overall ratio of boys to girl is, and that's what I'm going to reduce. Okay? But sometimes when we reduce, it's hard to take those things back up to scale and understand. Because these ratios, when I'm comparing two groups, okay? So a ratio, by definition, is just a comparing. Now those two groups might be parts of a bigger group. Like boys and girls are all part of the bigger group of students, okay? But I can compare stuff like Republicans and Democrats. They're very much not the same group, right? But they're really a big group of politicians. So a lot of times looking at that, it depends a lot on our perspective, on how we're seeing these two groups. Okay? So with that being that, my group doesn't even have to be a number of items. Okay? A ratio can even be a comparison between two units. Okay? That's why we use a general term like group. I can have something like covering 60 miles in 1 hour. Okay? This is a ratio. Typically, it's going to work in fraction function form, okay? But understanding that is a big deal and how I'm going to approach that. So now the context of the problem helps me understand what kind of a ratio I'm dealing with. All fractions are ratios, okay? But they are a subgroup of the bigger deal of ratios and rational numbers, okay? So anytime that I'm comparing these two groups, I'm writing a ratio. A proportion is comparing two ratios. Okay? So, we talked a little bit about this group, okay? Two separate classrooms, and I combined them. Did I compare them? Nope. But if I did want to compare them, that's when it becomes a proportion, okay? Now, these ratios typically come out to be equal. They have a consistent ratio between them, okay? And this is where it gets hard, like I was saying, about scaling things back up. You have this great idea, how do we actually get that to reapply to everybody, okay? So if I have something like 3 to 4 boys to girls in a setup or scenario, okay? If I want an equal proportion, and I've got 360 boys, and I don't know how many girls. We've seen a lot of these. Okay? These setups are the cross multiply and solve, because a lot of times these proportions and the ratios work the same way. Okay? And we're used to that, it's consistent, and it works out pretty nice for us. Okay? So being able to do that cross multiply, solve, and then you can find out how many girls there are. Okay? So that works out very nicely for us. Sometimes we get them in less than pleasant ways. This was my least favorite all throughout school. Here is our flagpole, and it is 25 feet tall. And the length of the shadow, do you remember problems like this? It just tortured me all the time. Is 40 feet. You are standing out in the field, and say at that time you're only 5 feet tall. There you are. How long is your shadow? This is where geometry starts to come in, because we see consistency between these two setups, the small triangle and the big triangle. Okay? How long are certain things supposed to be? And you can set up a proportion. So setting up the proportion was really the hardest part of this whole problem. Okay? And being able to set it up so that way I've got two fractions equal to each other. Okay? Now if I go back to this idea of boys and girls, notice that boys are always on top in this setup. Okay? And I have a comparison of boys to girls on there. Okay? So, having a similar reasoning, when I set this up, my top has to have something in common. Okay? Because these are the exact same kind of lengths, they're all foot lengths, okay? My unit isn't going to be the determining factor. I've got to look more at this picture. Okay? My top numbers here can either, one, come from the same triangle, and that's their connection, or two, be the same side of the triangle. Okay? So I can set this up a couple of different ways, but making sure that there's a relationship found in these numbers and then in these numbers. Okay? So these top two numbers, we can say, come from this triangle. Okay? So 25 feet and 40 feet. Okay? Now 25 has relation to both of these other two numbers. It really actually has no relation to our question mark. Okay? And that's one of the things that we have to help students see and understand about a proportion and how to set it up. If I've used within the same triangle, now 25 connects to 5 by both being the upright, shorter length of the triangle. Okay? So that is what goes here. So as I think about this circle, these are shorter lengths. These are from the same triangle. Okay? Well, that means that the bottoms both need to come from this triangle. If I've used 5 feet there, then that's where my question mark has to go. Okay? Now I've set up the proportion, I can cross multiply solve, all of it works out really nice and easy. Okay? But setting up and finding some kind of connection here and some kind of connection top to bottom that relates those two numbers. Doesn't mean that they're the same number, but they're coming from the same shape or the same setup, the same classroom. Okay? Just like this example though, three boys to 4 girls might be the general ratio, and I've got to then scale it back up to my bigger numbers. Because I know I have 360 boys, how many girls do I have? Okay? And being able to take some small piece of information that we abstractly understood and then apply it back to its context is a really hard thing for a lot of students to do. So that's why setting up these proportions correctly is a big deal for helping students in understanding how a proportion works and then how you can solve it.